Welcome everyone at the Basics of Flow Chemistry webinar series. This is the third presentation, and today we will talk about safety and how can you make your reaction safer with continuous flow technology, including our instruments, the ThalesNano instrument. So today's outline, we will talk about hydrogen safety in everyday laboratory practice. What are the safety considerations in lab practice? How traditional batch hydrogenations are implemented? How can you mitigate the risks of traditional hydrogenation? And how can flow chemistry increase the safety of a hydrogenation reaction? Of course, we will talk about on-demand gas generation, how to form gases via electrolysis or using chemical generators, and of course about the H-series instruments and their safety features. At the end of the presentation, I would like to talk briefly about multi-step and telescoped reactions and how can on-demand production be achievable, what are the advantages of telescoping, and how are automated platforms accessible for synthesis, and we will have a short outlook at the pharmaceutical industry in this field. So let's start with hydrogenation and hydrogen safety. As you all know, everyday laboratory practice is dangerous, so there are lots of dangers of fire, risk of explosion, especially when you are working with reagent gases and or hazardous materials, and of course extreme reaction conditions themselves can cause troubles in everyday laboratory practice. So naturally there are lots of national or international safety regulations which we have to take into consideration when working in laboratory, including the transportation, the use and the storage of chemical compounds. They are very strictly controlled and regulated by different laws, for example, the REACH and the CLP laws. Of course, safe conditions and processes are elementary and they must be followed to minimize all of the risks, including the human exposure to chemicals. And of course, avoiding fire and explosion is very important for all of us to prevent damage of property. On the picture you can see a tank explosion which happened in Midland Resource Recovery, which was unfortunately fatal. So that's why safe conditions have to be strictly followed. Traditional batch hydrogenation has lots of problems, and lots of them are connected with the hydrogen sources. So usually hydrogenations are performed with hydrogen gas coming from a hydrogen cylinder. The use of these cylinders requires trained personnel, so you have to be trained very carefully to be able to use these. And in many areas, this hydrogen storage and the method of using hydrogen is strictly controlled, and the hydrogen storage must be separated from the laboratory where you actually perform the reaction. In better cases, there are a central supply for hydrogen. Worst cases, you have to go into a completely different building to perform the hydrogenation reaction which you would like to have in your synthesis. This is because hydrogen is highly flammable and has a very big hazard of fire and explosion. The reactants and products which we are using for hydrogenation require almost every case is flammable solvents, and in many cases heterogeneous catalysts which are often pyrophoric. Therefore, when you are handling them, for example, try to filter out them from the reaction mixture. It can be very problematic. And when you are trying to scale up this process, of course, this can backfire. And in addition to that, reaction times can range from minutes to days. And the catalyst handling, of course, on larger scale is more problematic as well. So it's very important to mitigate these risks in connection with hydrogenation. So first, you will try to reduce the hydrogen quantity which you are using, so decreasing the amount of gas used and stored. A very good way to do this is to replace the gas cylinders with gas generators, and this will be the second topic of today. Of course, you have to somehow mitigate the risks with handling catalysts. So all standard operation protocols must be followed and must be handled by trained personnel. Flow chemistry can offer great advantages on this field. So catalyst can be applied loaded into catalyst columns with filters on both ends, and by this the catalyst will stay inside the tube, and the user does not have to get in contact with the catalyst. There are risks associated with the reaction vessel which you are using, so careful design is elementary here as well. And the operation, for example, the operation of an autoclave requires trained personnel again and high supervision as well. This can be mitigated by using other type of synthetic technologies, so moving from batch technologies to continuous flow will help to address this concern. So how to increase the safety in general when planning hydrogenation reactions or any other type of reactions, to be honest. So the careful planning is the first step you have to follow. It is crucial for the whole process. You can substitute the hazardous reagents if it's possible, and by this make the process safer. Or if it's not possible, you can minimize the used amount of the hazardous material. Of course, implementation in a safer environment, if it's feasible, can help a lot. That's why flow chemistry has a great advantages compared to batch processes. And if you are able to simplify your process, that will help a lot to increase the safety. You can decrease the number of the reaction steps with careful planning or using other type of reactions, and you can telescope these steps together, and this will be the third topic of today. So with this, you don't have to bother with intermediate workup or purification separately from the system. If you would like to know more details about this, please watch our first webinar, Basics of Flow Chemistry 1, because I have talked about it a lot, how to design these type of reactions at that webinar. So let's talk about on-demand gas generation for a bit. So with this, you don't have to store the gases, so they are generated on demand. And in the case of hydrogen, you will see we are using this electrolysis technology, and we are generating hydrogen from deionized water. And the main thing here is that this gas is consumed immediately in the reaction, so that's why no storage is needed. And by this, most of these regulatory requirements, how to store gases, can be reduced, so you don't have to bother with them. Reduction of gas quantity, of course, is important. So the amount of the generated gas in a given time is significantly lower compared to the cylinder which is standing in your laboratory. So in case of any kind of malfunction or unexpected events, there are a lower risk of fire or explosion because of the reduced gas quantity. As I told you before, there are two separate methods for gas generation in continuous flow processes. So the first is using a gas generator which works via electrolysis. Hydrogen and ozone can be obtained this way, or the chemical generator concept by Capes group is a very good example how to generate hazardous reagents in situ in a chemical reaction with continuous production. Of course, it can be applied for gases as well, and I have an example for you of that later. So let's talk about the electrolysis for a bit. So dedicated gas generators which use this principle are commercially available now. Most commonly, hydrogen, deuterium gas, and ozone are obtained via this way. Gases can be obtained from benign compounds, and the whole process has a very high control because of the hardware and software aided generators. So you will have a high control over the whole process as well. There are adjustable parameters. You can adjust the pressure, the gas amount, and the gas flow rates with these generators. And many of them have high pressure capability as well. So with this, you can work in a wider chemical parameter window. And with this, you have the option to choose what type of reaction vessel would you like to use. So with a hydrogen generator, you can use, for example, an autoclave, or you can fill up balloons, or you can use your flow reactor as well with this. And most of them come with automatic emergency protocols. So in case of any problems, the system will stop and stop the generation as well. So with this, it's safer than if you have any kind of problems during a batch reaction and you have the cylinder standing there. So with this, you will improve the safety of the whole laboratory. So more about these chemical generators. It's a very good way to obtain these hazardous compounds, and you can find the right reaction, how to obtain them for benign precursors and how to consume them in situ. So the basic concept can be seen on this slide. So you have your precursors and you generate the hazardous reagents, let be it, for example, chlorine gas. You have some kind of purification, so these in situ generated compounds have to be purified in order to use them in the upcoming reaction step. So this is the concept by Cappe's group, as I mentioned before, and I have an example for you. It's an example how to generate chlorine in situ in the reaction. So here they had sodium hypochlorite and hydrogen chloride. In this reaction, chlorine gas was generated and an organic solvent was pumped through this solution. The extraction took place in the next step, and with a membrane separator, the elimination of the aqueous waste was achieved, and after that, the chlorine was used in a subsequent reaction. So this is a very good example how these chemical generators look like in a system. And of course, it can be used for multi-step synthesis as well. That's part of a synthesis. So about the safe use of gases in flow. So lots of added benefits come from flow technology itself. So flow chemical systems are designed to withstand extreme process conditions in most cases, including high pressure as well. So the system itself will withstand high pressure and high temperature as well. Of course, high pressure is important because it can result in reaction rate acceleration, which is a very important thing when optimizing a reaction. And with flow systems, you will have a large interface area, and by this you can eliminate the headspace as well. So flow chemistry is very good from these, and important is also the mixing of the phases as well. Especially when you are performing hydrogenation. So if you have gas-liquid mixtures or gas-liquid-solid mixtures, the mixing is a very important part, and flow chemistry is very good at that. Of course, it comes with improved heat and mass transfer also, and with these systems you will have the precise reaction control. You can control all reaction parameters and of course the outcome of the reaction as well. So you can fine-tune, for example, a selective reaction with continuous flow technology, and it will give you easier optimization for all of these. And in the end, it can happen that you can perform the reaction at milder conditions in a separate reaction mechanism compared to the batch processes. So let me talk about the H-cube systems and the Agini hydrogen generator. So these are our generator systems coupled with continuous flow technology, which are very unique at the market. So ThalesNano's h-cube systems are the first instruments which are dedicated for hydrogenation in continuous flow. We have the Mini Plus and the h-cube Pro instruments. The h-cube Mini Plus is very easy to use, very safe and very straightforward reactor, mainly for routine reactions and for educational purposes. And the h-cube Pro is the instrument which is dedicated for advanced applications. So it's a very modular reactor. You can fine-tune and customize the system to meet your chemistry. And this system offers adjustable hydrogen amount, so you can adjust how many hydrogen would you like to apply in your reaction. And if you have a selective reaction, it's a very important feature. The h-genie system is our newest system. It is dedicated for larger scale hydrogen production and larger scale synthesis. It's a modular system, so you will have the hydrogen generator and the reactor separately, and you can build your own custom system with these and of course other modules which we are offering as well. The background of it is very interesting. So we had the limitations of traditional batch hydrogenations in our mind, and we felt the need to somehow solve this problem, and that's why the h-cube system, the first h-cube, was developed back in the early 2000s. So these reactors combine benchtop continuous flow reactors with hydrogen generation. Chemical transformations can be performed very easily with this. With the h-cube Pro system, up to 100 bar pressure and 150 Celsius degrees temperature, which is a bit wider compared to what you can obtain with an autoclave, for example, in a batch reaction. So with these, you can perform heterogeneous catalytic reactions as well. And the on-demand hydrogen generation is the most important feature of this system. So you will have only the amount of hydrogen which you would like to use in your reaction, and you will consume it immediately in your reactions. So how does it look like, these electrolytic cells and the on-demand generation? So this is a patented technology which we are using, especially designed for this system. And hydrogen gas is generated through the electrolytic splitting of water into electrolytic cells. So the water is applied at the anode side, it dissociates, and the protons are migrating through a membrane to the cathode, and there the protons are reduced to produce the hydrogen gas. Of course, oxygen is formed in this reaction as well, but oxygen and water residues are handled separately. So in the end, you will have a water separator unit which will remove any kind of residues of the generated hydrogen. So with this you will have high purity hydrogen gas, which you can then apply to your reaction. So here you can see the schematic view of the Mini Plus, because it's an easier and more straightforward instrument. I will guide you through the parts quickly. So you will have a micro HPLC pump seen at here, which is for ensuring the continuous stream of the starting material solutions or the pure solvent. The system will have an inlet pressure sensor to monitor any kind of pressure differences between the system pressure and the inlet pressure. So when you have overpressure, clogging, leakage, you will see it. There's a gas liquid mixer with a unique titanium fluid, which help the hydrogen to be dissolved in very little bubbles in the liquid stream. And from this point, you will have the gas-liquid mixture, which will enter the heater block, which contains the catalyst cartridge, and the reaction will take place on the surface on the catalyst. Of course, this catalyst cartridge can be heated up to 100 in the case of the milli plus 100 Celsius degrees, and 150 in the case of the HQ Pro. The catalyst column is pre-filled with the catalyst and contains filters at both ends, so the catalyst filtration is not needed in this process. And of course, you will have the back pressure regulator to obtain the high pressure for your reactions. In this case, it's maximum 100 bar pressure. Of course, lots of safety concerns and safety features had to be addressed and built into these systems. So let's start with the flow technology. So due to the nature of continuous flow reactions, you will have only a small amount of reaction mixture present in the system in a given time. So if anything goes wrong, you will only have this small amount of reaction mixture go to the waste. And you will have the starting material solution and the products you already have separately, so they will stay and don't worry about them. If the system pressure increases more than, in this case, 130 bar pressure, the system will automatically stop. And hydrogen will be released, all parameters will be set to the basic line, so room temperature and atmospheric pressure. So in case of leakage, blockage or hardware error, you won't have to worry about hydrogen being stored in the system because it will be released along with the pressure. They contain a built-in hydrogen sensor, so if you have a hydrogen leak, the system will automatically stop and give an error message to contact the service immediately. The water level from which the hydrogen is generated is constantly monitored in this system, so if the water level is too low, you will have the error message to fill the water tank up, and you can avoid with this the drying out of the hydrogen cells, and you can prolong the lifetime of the hydrogen cells by this. Of course, all catalyst cartridges are also designed to withstand high pressures exceeding 200 bar pressure in this case, and the hydrogen cell itself is designed to hold this 200 bar pressure as well. So this actually acts as a safety valve when we have overpressure in the system, so the hydrogen will be released in this case. Of course, in any kind of cell defect, the system will automatically stop again with an error message, and since all of our systems are recommended to be used in a fume hood, worst case scenario, you only have the amount of hydrogen generated in that time released, but a fume hood, a well-ventilated fume hood, can handle this amount of hydrogen. So with this, the danger of ignition is very decreased and almost negligibly small. Of course, because of continuous flow conditions, the reaction zone volume itself is significantly smaller than the requirements. And let me talk about a bit about the Phoenix Genie platform. So, as I mentioned before, it's a modular system designed for scaling up hydrogenation reactions. So it's a robust system. You can use it for catalyst testing and scale up as well. It's expandable and highly customizable. So you will have as many pumps, as many mass flow controllers, as many reactors as you like in your reaction. The whole system can be fully automated and controlled via our own software, or you can use LabVIEW integration with them. And of course, the on-demand hydrogenation is here the main main feature, and with the Genie you can reach up to 1 normal liter per minute hydrogen production rate, which is it's a very great number. So you can perform milligram to kilogram scale with this productivity. Let me talk about the h-genie a bit more. So it can be used as part of our platform system, but can be used for batch reactions as well. So you can fill up your autoclave or your balloon as well with the h-genie. So you can power up your complete laboratory with an h-genie, and it eliminates the needs of hydrogen cylinders. It has also an internal hydrogen detector. In case of any kind of hydrogen leakage, the system will automatically stop. You can reach 100 bar hydrogen pressure with this, and it's a very easy to use system, so it just click and go, and you can switch between batch flow or balloon applications. It has the ability to export the data which you have collected, and it's suitable for any fuel, so it's a compact size instrument. So as I told you before, it has safety features as well. So if the electricity, for example, is suddenly turned off, then the system will stop and release the hydrogen. It has built-in hydrogen sensors with the automatic shutdown function. It has water leak detection at the base of the instrument, so that if the water is leaking, the system will stop and tell you to contact the service. It has 3 fans, so the whole interior of the system is ventilated, and it can prevent the temperature rising or accumulation of hydrogen or oxygen in the inside of the system. When you power it up, it starts with self-checking for internal leaks, and it has a pressure limit as well, so it's maximized at 115 bar and controlled via pressure sensor. So if you exceed that overpressure, it will automatically stop and release all the hydrogen and the pressure as well. Just a few quick words about the Phoenix flow reactor. So this is the continuous flow reactor which we are offering to use with the h-genie system. It's a very unique system, so it can be heated up to 450 Celsius degrees. So it opens a very large parameter window for you to work in. It's compatible with corrosive agents as well. You can perform not just heterogeneous hydrogenation and catalysis, but homogeneous reactions as well. So you can use liquid-liquid, gas-liquid solid, or even just gas phase reactions as well. It is very quick for catalyst testing, or you can use it for scaling up your reactions. Very rapid heating and cooling is implemented with this system, and it's only a benchtop system, so it's a very compact system. It has safety features as well, so it can be started with the door open, for example. It has a separate pressure release valve as well, so in case of overpressure, the gas-liquid mixture or the liquid or the reaction mixture which you are using exits through this pressure release valve. It has temperature alarm, it has communication alarm, so if there's any kind of problem with communicating with the other modules, it will tell you. And it has a heat exchanger as well, so it can cool the outcoming liquid while preheat the reaction mixture before the reactor's on. So with the combination of the Genie and the Phoenix flow reactor, you will have a very unique system which can be implemented as a new standard for hydrogenation scale-up reactions. So finally, let me talk about a bit about multi-step reactions and on-demand production. Of course, in continuous flow. So let me talk about the safety features which come from the flow chemistry technology. So flow chemistry technology can improve the safety of both the user and the chemical process as well. The reagents can be handled completely separately, and if they are sensitive, it can be performed under inert atmosphere as well. The relatively small reactor volume can minimize the product loss in case of any unexpected events. So only the amount of reaction mixture present in the reactor will be lost. The starting material and the product will be intact. The reactions can be quenched very easily, so reactive intermediates and byproducts can be eliminated in a very easy way, and the workup can be implemented in a continuous flow manner as well. So if the whole process is designed carefully and can be carried out completely in a closed system, then the exposure of the user to these chemicals is minimal. It's a very safe process. I have mentioned briefly the packet bed reactors, which are used in the H-cube systems and the Phoenix flow reactor. So these heterogeneous catalysts can be loaded into these columns directly, and they can be used with our systems. They are sealed but have filters in it, so the liquid gas mixture will come through it, but the catalyst loading will stay inside, so you don't have to filter out, for example, the catalyst from the reaction mixture. That's why the exposure of the user to the catalyst is minimized, and with this, the safety concerns with handling catalyst can be minimized as well. So depending on the size of these columns and the catalyst loading, scale-up reactions can be performed also. And in the case of the Phoenix flow reactor, we have a very large variety of different volumed catalyst cartridges, so you can perform the first step of scale-up experiments with this same instrument. And we offer preloaded catalyst cartridges, so you just use our technology, and with this you don't even have to touch the catalyst itself. In case you are wondering if you can use your own catalyst, yes, you can. So you can fill them into our catalyst cartridges, or we can do it for you, and you can use your catalyst for testing or performing reactions as well in a safer manner. So why are multi-step synthesis and telescoping reaction steps advantages? So with these multi-step flow protocols, you can obtain your products without the isolation of the sensible or hazardous intermediates. With these, you can minimize the losses which come from working up the reaction mixture. If you are planning your reaction carefully and optimizing it, your reaction times can be reduced significantly. And with the integration of inline analytical methods and purifications, you will have the whole process performed in continuous flow, and of course you can automate the full process. So, as I have mentioned before, implementing such a process requires careful planning, and you have to take into consideration all reaction parameters as well, starting with the instrumentation which you would like to use, what type of reactors, how many reactors, and you have to consider the material which the reactor is made from as well. You have to choose the right solvent or solvents for your reaction. You have to optimize the temperature and the pressure of the individual reaction steps to be compatible with each other and to obtain the highest yield which can be obtained. And of course you have to plan how to remove the byproducts which might cause troubles in the next reaction step, and how to add the new reagents into the next reaction step. So this is pointing towards on-demand production, this all, and let me take a small detour into the pharmaceutical industry, because this is the field I'm involved the more. So in accordance with FDA's newest recommendations and vision for drug manufacturing in the upcoming years, more and more API synthetic processes and drug manufacturing production is implemented in continuous flow. We have seen very good examples, for example, the synthesis of artemisinin or rufinamide, which is implemented completely in continuous flow, including all the parameters, the optimization, the inline purification, and workup method as well. So with on-demand production, the production can be performed on-site, so you can produce the drugs where they are needed, and with this you can eliminate all the issues in connection with the transportation and storage as well. So on-demand production will eliminate the need of drug storage, and by this you can overcome of any kind of drug shortages in the future. And a dedicated instrument for dedicated drug production can reduce costs of manufacturing significantly as well. So other advantages include the reconfiguration of these kind of systems. So it's a main goal to have such synthetic devices which can perform several different types of syntheses with the same instrumentation. So you can obtain different type of APIs, for example, with one system. And the whole point is here to make the operation of such systems safer and easier. And if complete automation is achievable, then the risks and the handling of these instruments and the whole process becomes much easier when automated. And for the very last, I would like to show you an example how it is done today. So Andrea Adamo has published a very groundbreaking system in 2016. So they have designed, Adamo and his co-workers, a complete system which is it's a very complete size, as you can see on the picture, and which is capable to produce 4 different APIs with one system. So you can see those APIs there. It's a very flexible and reconfigurable system. So they have the parts dedicated for different type of reactions, different workup methods and purification methods. And with this, they can adjust the system for each synthetic process and decide which type of API to synthesize on-site and on-demand. It's a very flexible system and integrates several types of inline purification methods and workup as well, and a semi-batch crystallization method, which helps to access formulated drugs at the end. Of course, the whole process is real-time monitored, and you have a complete software to handle all parts of the system. But it's a very good example how continuous manufacturing can overcome our problems with drug manufacturing. And I think it's a very good example how to, for example, put this system in an area where drugs shortage are present, and just synthesize on demand the amount of drugs which will be used. And as I mentioned before, with this you can eliminate the problems of large manufacturing time, transportation and storage, and it's very important in the case of short lifetime drugs. So when you are synthesizing them on demand and use them on demand, it's not a problem in the short lifetime. So for further reading, I would like to draw your attention to the new flow chemistry textbook, which contains a dedicated chapter, how to mitigate chemical hazards under continuous flow reactions. If you are interested in chemical generators and the whole concept and how to obtain hazardous materials in situ in the reaction, I would like to draw your attention to the Kappa group's achievements. If you would like to read about designing multi-step continuous flow reactions, I have a very good publication to show you. And of course, I would like to show you again the on-demand production in continuous flow, which is a very good publication by Andrea Adamo as well. So thank you for your attention, and if you have any questions, please feel free to use the YouTube chat box. I will be here to answer your questions, and if you have any other questions, you can also contact us at askthechemist@thalesnano.com as well. So thank you again, and I will wait for your questions. So thank you again for your attention, and if you have any questions, please do not hesitate to ask us in the chat box of the YouTube. I have one question. What is the maximum volume of these catalyst cartridges? So for the Phoenix flow reactor, we have different type of pre-filled and empty catalyst cartridges which you can use. So it's a very diverse range, and you can go from around 1 milliliter volume to a maximum of 80 milliliter volume. This is a very big catalyst cartridge. And for the H-cube systems, the smaller one, the 30 millimeter long cat cards, have an inner volume of around 3 milliliter. 300 microliter, and for the 70 millimeter cat cards, it's around 800 microliter volume. Any other questions? Oh, I have one more. How can custom catalysts used in the systems? So for the H-cube systems, we have a cat packer instrument. This is a mechanical instrument to allow you to fill your catalyst inside our catalyst cartridges. So you can order the tubes from us and fill with this cat packer instrument your catalyst inside the tube, and actually seal it and then use it in the system. If you would like to use the Phoenix flow reactor, of course, you can use cat cards as well, or you can use the empty metal sealed cartridges, which you can fill for yourself. So they come empty. If you don't like to fill it for yourself, we have this cat card loading service. So you can send your catalyst to us, and we can fill the catalyst inside the cat cards used with the H-cube systems. Any other questions? You can use the YouTube chat box as well. If you have longer questions, you can write us to askthechemist@ThalesNano.com as well, and we will answer it. Still waiting for questions. If you have any, please do not hesitate to ask. Okay, if there's no other questions, then thank you for your attention again, and see you in the next webinar. Thank you very much.